Oops, for Kenneth, everybody say hi, Kenneth. Hey, let's try that again like you mean it. There we go. Okay. So our goal for today is twofold. First of all, I'm going to talk a little bit about averaging function. And then having done that, we're going to apply that to get our first part of the fundamental theorem of calculus, in which we will discover that, in fact, Riemann sums provide us with solutions to differential equations. Somebody tell me, how do you average a bunch of numbers? I have a bunch of numbers. And we'll call those numbers y. Exactly so. And I would write that like this. The average, which we will call y average or y bar sometimes, you'll see it written like that, but we're going to call it y average, is the sum, y equals 1 to n, of yi, and all of that divided by n. And all of that is a fancy way of saying add them up and divide by n. So now, what if, though, I wish to find an average, but I don't have the time or the resources to go and get each individual data point? For example, suppose I wanted to get the average height of a CCA student, but to actually go through all of 370-ish CCA students and get their heights, add them all up, divide by however many ever, would be a pain in the neck. What would I do?
Will you need that textbook?
Nope. Well, you can't solve it by staring at me. Let me make it more concrete. Let's suppose that it costs you $1 each time that you ask somebody for their height, and you only have $20 research price. Okay. So we can take shortest person and tallest person and find the midpoint of those. And when you do, is that the exact average? Is it an estimate of the average? Yes, it is. Is it a particularly good estimate of the average? How would you improve your estimate? You need more data. That's right. So you would take more points. And so if your budget is $20, then you could actually go through and you could choose 20 people. And if you're thinking about it smartly, you might not just want to choose 20 people off the street. You might. But you might want to, like, go to different classrooms where there might be different grades of people, and you might want to sample out of that classroom, and you would want to pick somebody probably at random. So all of this means that if I want to estimate an average, then I do the exact same procedure, but I sample from the entire population. By sampling, and then I'm going to say that my y average, in statistics you probably use mu for the average of the population. So, and you would use y average for, or y bar for the sample, right? And so then we have y average is approximately equal to the true sample, excuse me, the true population mean. And in statistics, where you go from here, is you now go into questions about how good is my estimate anyway, and that leads you into like standard deviations and t-tests and stuff. Okay. But where we want to go with this is we want to ask this question. As soon as you're ready. Hello, Philip. We want to ask this question. What is the average value or height of f of x on the interval a to b? What is the average value of f of x on the interval a to b? And the picture that we're going for is I've got a function f of x and I've got an interval a to b. And what I'd like to do is to find the average of all these heights right here. And I think we all agree that it is impossible for me to directly add up all the y values and divide by the total number of y values because there are an infinite number of each. Can't do that. So what I'm going to do instead is to sample my function by partitioning a to b with a regular partition. So that delta x is equal to b minus a over n. And then I'm going to go through and I'm going to sample one y value, f of x value, out of each partition. How will I choose that x value? I actually don't care. I can make it a right-hand sample, or I can make it a left-hand sample, or I could make it a midpoint sample, or I could make it a randomly chosen sample. Doesn't matter. I'm going to choose one x value c sub I out of each subinterval xi minus 1 to xi. And then what I do, f average is going to be approximately equal to the sum from I equals 1 to n of f of ci. All of that divided by n. Ta-da! I've just averaged my function. But notice the approximately equal. And the approximately equal comes about because I have not included the entire population of y values. I've only included a sample out of the possible y values. How would I improve my sample? My estimate, I would improve it by letting the number of y values go. But before I do that, I want to pretty this up just a little bit because this really reminds us of something. What does it remind us of? You guys need to be thinking about something. What does it remind you of? Of course it reminds you of the one sums. Absolutely. But the problem is that we're missing a delta x right here, and we've got this funky n thing going on back here. So what can we possibly do with that? Well, I don't know about you, but what I observe is that the n that I have is related to the delta x. And in particular, I see that delta x over b minus a is exactly the same as 1 over n, which is what I have right here. So that times 1 over n is the same as times delta x over b minus a. And this is outside the sum, but because of some properties, I can distribute the delta x, and I'm going to pull the b minus a off to the side here, because now what I have is a genuine straight-up Riemann sum. What is this telling me? This is telling me that if I take a good old-fashioned Riemann sum, and I choose the CI however I wish, by sampling in each interval, like so. Like that. Then my Riemann sum, which computes the area here, divided by the width b minus a gives me an estimate of the average height. And the picture that we have is that my average height multiplied by b minus a gives me the area of a rectangle like this, and the area of this rectangle just so happens to equal the area under the curve. So that this rectangle right here is a one rectangle estimate of the area of the function. So it happens to be a pretty good one because its height is determined by the average height. Well, I can now make this average perfect by letting the width of my delta x go to 0. Because as the width of delta x goes to 0, each one of my rectangles now only has one choice for its sample value, and that's f of x at that point. You see what I'm saying? So that by letting delta x go to 0, I will now be including 100% of my function values in the sample, and I now have the true population mean. So that f average is going to be exactly equal to 1 over b minus a times the limit as n goes to infinity of the sum from I equals 1 to n of fci delta x, which is a definite interval. And boom, I have my average value. That's a little better. Okay. So we have our average value. Question.
Did we ever discuss what the difference was between the limit as n goes to infinity and the limit as n goes to here?
We slightly did, and the difference is this. This is the official way to make this happen. The Riemann sum, the definite interval is the limit as n size goes to 0 Riemann sum. But if it so happens that my delta x is regular or in some way a function of n, so that as n goes to infinity, delta x goes to 0, then I can make this happen by making n go to infinity.
Okay.
The case where it would not happen is, remember that weird partition we had with delta xi equals 2 to the minus I? In that case, my n can go to infinity without mesh size going to 0. Okay, so what is the point of the f average? We want to think of the f average as being the average height. And it turns out that averaging f is an extraordinarily powerful tool. And the reason it's an extraordinarily powerful tool is that what this does for me is it allows me to, instead of dealing with all of my different function values over an entire interval, I can replace that with a single number. In particular, there are 3 things about f average that I want you to know, and all of them are easy facts. First fact is a simple matter of multiplying both sides. The net signed area under f is easily computed as f average times b minus a. And that literally is a matter of multiplying both sides of the definition by b minus a. What this means is that if I happen to know the average value, I can find the net signed area under the curve with simple multiplication instead of having to hit it. Second fact. This is intuitively obvious, but sometimes people forget it. the average value can be no smaller than min value, and it can be no larger than that side. People without good number sense will sometimes forget this, and they'll like average up a bunch of numbers, average up a bunch of grades, and end up with an average that's like 108. And they're like, aren't the grades from 0 to 100? Well, yeah. Okay. So why is this true? This is actually true because of our min-max property. Remember that the integral itself is trapped between f min times b minus a and f max times b minus a. This is our one rectangle lower sum, and this is our one rectangle upper sum right here. Well, if I divide through by b minus a, then I get this, and lo and behold, this is exactly f average. And third and final point, if my function happens to be continuous, then there is a C in A to B such that f of C equals f average. Continuous functions hit their average values. This is sometimes called the average value theorem. It is usually explicitly expressed as f of C equals 1 over b minus a, integral from a to b of f of cx. And the proof actually is really simple. Simple observations. Property number 2, f average is between f min and f max. F is continuous. Bust out the intermediate value theorem. We are guaranteed a C so that f of C is equal to f average. By the intermediate value theorem. In other words, the picture is this. If I have my continuous function from a to b, here's f min, here's f max, my f average is going to be some height that is between here and there, so that the area under the curve, which is in red, is exactly equal to the area under the rectangle, which is in blue. And this average height has to go through the curve at some point, simply because the curve is continuous. I want you to observe that this is a more powerful theorem than the mean value theorem for a simple reason. It doesn't require differentiability. It's related to the mean value theorem, but it is not. But it is stronger because the conditions are weaker. F does not have to be differentiable in order to satisfy this thing. Practical thing, when you're finding average values on a graph, I want you to notice that a great way to identify whether or not you've got a good average value is that all of the area that is above your average value and all of the area that is below your average value should cancel out. Does that make sense to everybody? So the way that I identify this is I sort of eyeball it by moving my line up and down until I've got equal areas above and below. Boy, those jumping jacks didn't last long. Charlie's back at it again. One great way to engage, by the way, is that whole note-taking thing. All right. Now we come to the big story of today, which is the fundamental theorem of calculus. And to get there, what I would like to do is to introduce the idea of an accumulator function. And an accumulator function is going to be a function in the form of an integral. What we have is some function f, graph shown here, and we're going to pick a starting point A, shown here. Notice that the starting point A is a fixed constant. Such as 0 or 2 or the square root of e. And now what we're going to do to generate our function of x is we're going to consider all possible x values along this line here. Here's one right here. And we're going to integrate out from a out to x and find the net signed area under the curve right there. And this area is equal to the value of a of x, just like that. So what a of x is doing is it is accumulating area as x moves this way or that way. Notice that if f happens to be a derivative, then I am accumulating rate times time, and that should give me some kind of distance idea. So if, for example, f represents velocity, then I will be adding up rate times time to get a displacement. So the accumulator function accumulates a rate. And I want to make some observations out of the accumulator functions before we get really started. One of those observations is that if I evaluate the accumulator function at the starting point, I always get 0. Sort of an obvious point, but you gotta make it. The second observation that I want to make is that if x is less than a, notice what that looks like. That means I'm picking a point back over here. I'm integrating backwards. If x is less than a, then a of x will be equal to the opposite of the net signed area from x to a. In other words, I can switch the limits and take the opposite, which is a familiar process for you guys. So evaluating the accumulator function for x is less than a is a matter of basically letting dt be negative and integrating in the reverse direction. And the third observation is just a practical one. There are functions that are similar to accumulator functions, but they're not exactly accumulator functions, and you gotta watch those. So we'll call these pseudo-accumulator functions. them can be rewritten as accumulators. So this will happen sometimes. This is a pseudo accumulator right here. I'm integrating, instead of having a fixed point A and integrating out to X, I am integrating backwards from the fixed point A back to X. But I can turn that into an accumulator function pretty quickly, just using my integral properties, right? Or we might have this one. This is a pseudo accumulator because it is not exactly integrating out to X, but it's integrating out to X squared. What does that even mean? Well, what that really means is I first take an X value, then I square, and then I accumulate out to X squared. So we could rewrite this in terms of some kind of substitution. So this is really a compound function. It is a function of X squared rather than a function of X. Yeah, exactly, that's right. I've got an accumulator times -1. I've got an accumulator with the substitution. Okay? With all of that said, now I want to ask the important calculus question. What is the rate of change of this accumulator function? What is its derivative? And I claim that at any point x, the rate at which the accumulation is changing is the Heisenberg derivative of x. That's what I claim. Ah, that's a really good question. Actually, it does exactly have to be in terms of that value of x. Right, yes, that's a really good point, and I think the proof will illumine the answer to your question. Let's go through the proof and let's see. So, let's actually prove this thing. We'll get ourselves a good function here. What we've got is a t-axis, and we've got an f of t, like so. And notice that I've made f of t continuous here. Does that matter? We worry about that. Let's assume for the moment that f of t is continuous, and then we'll come back and address that question later. Okay. Now, the first part of the answer to your question, Lydia, is that x is going to be a value on the t-axis, at a particular point on the t-axis. So what I'm doing is I'm adding up values of f along the t-axis from a out to x. And so the actual variable of my accumulator function is found right here, not right here. This guy could easily be s or p or any other variable, because it's just a matter of labeling these guys, and then the real action happens between a and x. So we call this variable inside here sometimes a dummy variable, because its identity does not matter, as long as I don't call it x, because that would confuse matters. Right? Now, not only would it confuse matters, but then we'd be like, whoa, what's this rate of change thing all about? Okay. Now, the way that I'm going to proceed is a very familiar pattern, proof pattern. I'm going to start with the left-hand side and get it to be the right-hand side. So we're going to start with the left-hand side here, the rate of change of our accumulator function. And now we're going to rewrite that as a limit definition, because that's the only thing we know to do. We'll take the limit as h goes to 0 of, this is awkward, but it's kind of interesting. So what I'm doing is evaluating my accumulator at x plus h, evaluating at x, and subtracting all of that over h. And now we wonder, can I possibly simplify this at all? Well, I can, because whether h is on this side or this side, it doesn't really matter, but I can rewrite this guy as the integral from a to x plus the integral from x to x plus h. So that when I subtract the integral from a to x, just take a look at the picture right here. Let's take h to be positive here. So this is the point x plus h right there. And the integral from a to x represents all of this area. And the integral from a to x plus h represents all of this area. And now when I subtract, what I am left with is just this area right here. Just that little tiny rectangle. And it is tiny because h is going to be a number close to 0. So that the whole top now simplifies to this integral right here. Everybody with me so far? I'm appealing to the graph to make it make sense. Trying to tell you pictures. And now something wonderful happens. What I'm going to do is to replace this integral, as we discussed before, with the average value of f times the width of the integral. The average value of f is going to be taken over just the interval x to x plus h, because that's my limits of integration right here. And the width of that interval is just h. Sure. Remember back when we talked about average value, back over here, that one of the three things that I mentioned is that I can replace an integral with average value times width. And that's exactly what I'm doing back over here. Instead of integrating, I'm just going to have an average value. Am I guaranteed there's an average value? Yes, because I've assumed f is continuous. And I'm going to replace that integral with the green, which is average value. Yes. And now something wonderful happens, and the h is canceled. Now, this is a really interesting expression. The limit as h goes to 0 of f average. Work with me on this a little bit. Since h is going to 0, what I am doing is taking all of the x values from x to x plus h, and f average is going to be, if I choose a c somewhere in here, f average is going to be equal to f of c for some c between x and x plus h. If h goes to 0, I only have one choice for c. It's got to be x. And that means, therefore, that this limit, as h goes to 0 of f average, is equal to f of x. Leibniz, as usual, has the really powerful picture here. Leibniz is going to picture it like this. He's going to say that what the accumulator function does is to give me area. And if I take area here, and I divide it by width, what I have to get is height. And if my width is shrinking to 0, the height that I have to get is the height of the curve f. That's it. So Leibniz is thinking of the little tiny sliver whose width is dx and whose height is f of x. He's saying the rate at which my area is accumulating is equal to f of x dx divided by dx. That's it. That picture is not, the math expressed there is not very rigorous. This is a rigorous math, but it sure does give us a really powerful picture. Now, among other things, observe what this means. This means that if I pick a point A like so, then as long as my curve f of t is positive, then I will continue to accumulate positive area, and my accumulator function will be an increasing function. So on this interval, right here, all throughout here, a of x will be increasing. And then, on this interval right here, as my function, as my curve goes below, this will take away from my net sum area, so that my accumulator function will now be a decreasing function for all the x's right there. Where will it have its max? Right when its derivative changes signs from plus to minus. The accumulator function will have its maximum value right there. At least it will. Why? In the picture, because I stop accumulating positive area and start accumulating negative area. In the analysis, because a prime equals f of x changes signs from plus to minus. Isn't that beautiful? Beautiful. Maybe you think it's boring. You guys all saw it coming. Got it? Where? Where are you at? Here. Oh, why do I do this? Is really what you're asking. Oh, because I'm looking for a derivative. And the derivative should be of a, should be the limit as h goes to 0 of this. Okay? And a of x plus h is going to be the integral from little a of x plus h of a to b. Okay? All better? Good. Good question. Anybody else?
Can you explain again how you got like f of x, like further down? Yeah.
Doom, doom, doom. Yep. Okay, so first of all, I replace the integral with average times width. Now, this is the key point, so you're really tracking right there. My interval from x to x plus h is a very tiny interval right there. And the average value has to occur somewhere in x to x plus h. If h now goes to 0, squeeze my c, because my c is between x and x plus h, then as h goes to 0, my c has to equal x. So it's really squeezed here. It's really happening there. And notice that we did rely on the fact that f was continuous. So we're going to include that as a condition. FTC 1 is going to be valid only if f is known to be a continuous function. we could relax that a little bit and say, except at that f could be piecewise continuous. But I think that would make things a little bit weird. I'll come back to that another time. Now, our payoff is this. We now have a way to write a solution for any differential equation in the form dy dx equals f of x. If we have a differential equation with an initial condition given, like so, then I can write y is equal to the initial condition plus the accumulator function from x to 0 to x. And notice the use of the dummy variable. And the proof is really simple. All I have to do is to check that my solution here satisfies these two conditions. If I evaluate y of x0 as specified, then I get y0 plus the integral from x0 to x0 of f of t dt. But that's 0, and the initial condition is satisfied. Ta-da. And furthermore, if I compute y prime, then the derivative of y0 is of course 0 because that's a fixed constant. And the derivative of my accumulator function, according to fundamental theorem, is equal to f of x. And lo and behold, I have satisfied the differential equation. So what this does for me now is it allows for me to write a solution to my differential equation no matter what function my derivative is equal to. That's amazingly powerful. You say, well, what good would it do me if I can't find an antiderivative? It would do you good in this way. Let's suppose you have a computer, and your computer could carry out this integration numerically by estimating with a large number of rectangles. In that case, you would be able to find a numeric solution to your differential equation at every single point x. You wouldn't get a closed form equation for it, but you would have a graph of your solution. That's close enough, isn't it? For scientific work, we consider that to be close enough. Does that make sense? In fact, we have just enough time. We're going to actually graph one of these things. So get your calculators out. And we're going to solve dy dx equals sine of x squared with y of 0 equals 2. And first we're going to construct the solution by hand by saying y of x is equal to 2 plus the integral from 0 to x of sine t squared dt. Ta-da. And now we're going to graph it. By letting, that's not the one I wanted, this is the one I wanted. By letting y1 equal 2 plus the integral from 0 to x of sine t squared dt. Now your calculator only knows the variable x, so we're going to have to just accommodate that. It's kind of silly. It's not great math, but it'll do. So we're going to let y1 equal 2 plus. And now here we're going to go to the integral under math. Math function number 9, right there. We're going to integrate from 0 to x of sine x squared dx. and graph that bad boy. Up, error syntax go to. Up, no, it has a table. Up, and it's graphing. Ta-da. It's graphing it really slowly. Why? Because at each point x, it's having to compute an integral. It's having to do 10,000 rectangles, actually 100,000 rectangles at every single point. So it's a really slow graph, and it's probably not going to finish before Miss Johnson's algebra class starts. Nevertheless, eventually we end up with a graph of our solution. And that's kind of so we'll pick this up again tomorrow. See ya.
All about the solution.